Hey guys, so in this video we're going to be learning about sequences. Um, the word sequence is pretty familiar to most of you, I'm sure. In mathematics we think of a sequence as a list of numbers. And so over here, this is a list of numbers 2, 4, 6, 8, and so on. And then each of these numbers in the sequence is called a term. We use a sub n to represent the nth term in a sequence, where n is any natural number. And remember, the natural numbers are your counting numbers, like 1, 2, 3, 4, and so on. And so, for example, a sub 1 would mean the first term. A sub 2 would be the second term, and so on. So in this video, we're going to be listing terms of sequences. We're also going to be trying to figure out a formula for a sequence, and then we'll be doing an application. So just to say, I guess starting off, a finite sequence is a function whose domain is the set of positive integers less than or equal to some fixed positive integer. So for example, when you have this kind of sequence, if it's a finite sequence, it starts and stops, okay? So like on this one, these are finite sequences because it's saying we're going to have a sub n equal to n squared, but we're going to start with a sub 1 and go to a sub 5. So we're going to just start a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. That's a finite sequence. An infinite sequence is one where it doesn't stop. And so it just keeps going and going, kind of like the one we showed up here. If I have like the dot, 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 right? It doesn't stop. This would be, all the even numbers on and on. Okay, so again, example 1, we're going to start by finding, it says, list the terms of a finite sequence. So for A, what you're going to do is just plug in a 1. You're going to start at 1, and you're going to go all the way to 5. So if we start with a sub 1, notice n is equal to 1. So now we plug in 1 into n here, so that's 1 squared. And 1 squared is 1. And then do a sub 2. So that would be 2 squared, and that's 4. A sub 3. That's 3 squared, which is 9. And then we'll keep going. A sub 4 is 4 squared, which is 16. And a sub 5 is 5 squared, which is 25. And so we've just listed the first 5 terms of the sequence. For B, here's the nth term. It's defined by 1 over n plus 2, and it wants us to go from 1 to 3. So we're only going to list the first 3 terms of the sequence. So for a sub 1, again, I'm going to plug in a 1 for the n, so this would be 1 over 1 plus 2, which is 1 over 3. And then I'm going to do a sub 2. That's 1 over 2 plus 2, which is 1 over 4. And then finally, a sub 3, that's 1 over 3 plus 2, which is 1 over 5. So those are examples of just listing the terms of a finite sequence. So you're going to be doing that. Example 2 is listing the terms of an infinite sequence. So let's look at that one. So here it says we have an infinite sequence, and it's defined as negative 1 to the nth power and then 2 to the n plus 1. But in the instructions it just says, even though this is going to be representing an infinite sequence, it just asks us to write the first 3 terms of the sequence. And then we're just going to add that dot, dot, dot to just show that it continues on. Okay? So let's start with a sub 1. So a sub 1 is negative 1 to the first power over 2 to the 1 plus 1. So you can see on here, negative 1 to the first power is negative 1. So this is going to be a negative to start. Our first term is going to have a negative. And then this is 2 to the 2 to the second power. Okay, so we have negative 1 over 2 to the second power is 4. So that's our first term. A sub 2. Do negative 1 to the second power, right? Where n equals 2. And then you're going to go 2 to the, and then n plus 1, so this is 2 plus 1. So here we have negative 1 times negative 1 is positive 1. So we have a 1 over a 2 to the third. And so that will be 1/8. Okay? And then the third one, the last one that we have to list, is a sub 3, the third term, negative 1 to the third power over 2 to the 3 plus 1. Okay? Negative 1 to an odd power, negative 1 times negative 1 times negative 1, that's negative 1. And then 2 to the fourth power, okay, is this is the third power, was 8. So now do another 2 times 2 again. So this is 16. So now we have our three terms, and then when we want to write it as an infinite sequence, we're going to write it as negative 1/4, comma, and then 1/8, comma, negative 1/16, comma, dot, dot, dot. So that is writing our infinite sequence, basically. We're going to just find maybe the first three terms or so, and then just show comma, dot, 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 that it continues on. So now, example 3, this one is finding a formula for the nth term. And so on here it says a familiar sequence, 3, 5, 7, 9, 11, dot, 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 comma, dot, dot, dot. It says find the general term for the infinite sequence there. So basically, one of the things that it does to describe, I guess, how to find it, is to think of what the even numbers would be. Even numbers are all multiples of 2. So even numbers you could represent with 2n. 2 times 1 would be 2. 2 times 2 would be 4, and so on. So they're saying, okay, for the even numbers then, 2 times 1 would be 2. We could adjust this formula by adding a 1 to this, and then it would make it odd numbers. So 2n plus 1. So now if I thought about that, I could see if this works. So 2 times, if I did this a sub 1, 2 times 1 plus 1, would that equal the first term in our sequence? So 2 plus 1 is 3. Yes. A sub 2, that would be 2 times 2 plus 1. And does that equal 5? Yes, it does, because this is 4 plus 1. So we can try one more. A sub 3, that would be 2 times 3 plus 1. And that would be 6 plus 1. Oh, sorry. So that's what they're saying on here is basically that you could think of the even numbers as a multiple of 2. So that would be 2n. And then the odd numbers, you could adjust it by just adding a 1 to that. This would be the odd numbers. Another way I think of it is if I look how each one changes. I think, okay, I'm adding a 2, I'm adding a 2, and so on, right? So that number right there, for me, it tells me what to put in front of the variable. So I think 2n, and then I just adjust that to try to create the first number. So if I thought 2 times 1 then I'd go, okay, how do I get to 3? I'd add a 1. So that's kind of how I do it. But that's example 3. Okay. Example 4 is writing a sequence with alternating signs. So they show you this sequence and they go, okay, it's 1, negative 1 over 4, then it's positive 1/9, then it's negative 1/16, and so on. So the way you can represent alternate signs is actually using powers of -1. We can actually use, I'll just say powers of -1 for alternating signs. Okay, so sometimes you can use, -1 to the nth power. If it starts off as a negative, use that. If it starts off as a positive, though, then you can use -1 to the n plus 1. Okay, because if you think about it, -1 to the first power would give you -1. So that would make sense for it starting off as a negative. But -1 to the 1 plus 1, okay, that would be -1 to the second power. That's going to be an even power, which is going to make it -1 to the second power is going to be +1. And that's what we start off with. We start off with a positive, okay? And then the only other thing you have to think of is what about these numbers on the bottom? So maybe in your mind, just think, this is also 1 over 1. So it's like going from 1 to 4 to 9 to 16. So in your mind, go, okay, well, that reminds me of perfect squares, okay? And we kind of did one back in the first example. Let's look back up here. In this example, to show perfect squares, 1, 4, 9, 16, 25, those were represented by n squared. So that's what we're going to use for this. And then we're going to add in the fact that we've got alternating signs. So for the nth term, you would say -1, and then to the n plus 1, because we're talking about starting off with a positive number. So that's what we're going to use, starting with the positive. And then where do we get our perfect squares? Well, they're on the bottom. So that's why we're going to divide by n squared. And that's actually going to make sense then. If you were to plug in a 1, then a 2, then a 3, you would end up getting these numbers. So for the very last example, all that's left on this, in your book anyway, is going over an application. So on here it says the bouncing ball. So you have, it says, suppose a ball always rebounds 2/3 of the height from which it falls, and the ball is dropped from a height of 6 feet. Write a sequence whose terms are the heights from which the ball falls. And then what's the formula for the nth term? So think about, the first term is 6. It's dropped from a height of 6 feet. Then the next one is 2/3 of 6, is what it says. It always rebounds 2/3 of the height. So then what's 2/3 of 6? Well, 1/3 of 6 is 2. And then 2/3 would be 4. And then you would try to find the next one. So then multiply this by 2/3 and you'll get the next term. So if we do 4 times 2/3, think 4 times 2, and then you have the 3 on the bottom. Okay? And then if we did it one more time, if we multiply this by 2, we get 16. Multiply this by 3, and we get 9. And then it would just keep going. Okay? So they want you to write a formula for this. Okay? And so this time, this is a geometric sequence here. We're multiplying. We'll learn about this later, but we're multiplying by something every single time to get the next term. Okay? We're multiplying by 2/3. because it's 2/3 of each one, and it starts at 6. So there's a way to actually write a formula for this. So you're going to be using powers of 2/3. So we think, okay, 2/3, and then we have to think, what power do we put this to? Are we going to do, n plus 1, n minus 1? This is where you have to kind of think about that. If n equals 1, what's going to happen? So I'll come over here and I'll just say when n equals 1, then you would have 2/3, okay? If you made it n, then that would be 2/3 to the first power, but the first term starts off as a 6, and so we don't want to multiply it by that 2/3 yet. Okay, so to the nth power is actually not quite what we want. So what they do is, since it starts off at 6, they do 2/3 to the n minus 1. Okay, and if we do that, when n equals 1, we're going to get 2/3 to the 1 minus 1 would be 0. And that, remember, anything raised to the 0th power is 1. And so if we think about, okay, I like that better because I'm not multiplying by the 2/3 on the first term, okay? So we're actually going to use to the n minus 1. And then just to figure out, well, how do we get the 6? If we actually multiply that expression by 6, we're going to get the nth term. So if I do, for example, a sub 1, that would be 6 times 2/3, and again, to the 1 minus 1, that would be 6 times 1, because this is 2/3 to the 0th power. So 6 times 1, which is 6. That works, right? A sub 2, try that. 6 times 2/3, and again, this would be 2 minus 1, which would be 6 times 2/3. And then, oh yeah, 1/3 of 6 is 2, and 2 times 2 is 4. And so you can see we're getting our sequence now, okay? So that's what you'll be doing on this set when you practice your work in here. You'll be writing the terms out, you'll be finding formulas for the nth term, and you'll also be applying a little bit to maybe a ball or something like that. So I hope this helps, and see you in the next lesson.